So my name is Andy Bocarsley. I'm teaching this course on electrochemistry, and I'm a professor of chemistry at Princeton University. Just to give you a second of background before we get started here, although when people ask me where I'm from, I tell them New Jersey these days. In fact, I spent the first 22 years of my life in LA. I was an undergraduate at UCLA, so I'm somewhat familiar with the area. And then after graduating from UCLA, I went to the East Coast where I've stayed, but the first stop was MIT for my graduate work, and I was in Mark Wrighton's group doing photoelectrochemistry with various people, but one of them that showed up about a year after I arrived at MIT was Nate Lewis. So I had the pleasure of teaching him a little bit about photoelectrochemistry, actually. And that is actually a subject that I'm going to try and stay away from this term. We're going to deal with the other aspects of electrochemistry, since Nate has a wonderful course going on if you want to hear about that. So we'll think about things that happen at metal electrodes and stay away from semiconductors, unless you want me to talk about semiconductors a little bit. I don't know. We can arrange that. What I'd like to do is, the course textbook is Bard and Faulkner's book, which is now in its second edition. This is a great book for learning the physical chemistry of electrochemistry. It's the second edition is much better in terms of examples, also actual real-life molecules that you might do something with. A dramatic improvement in the book there, so it's good from that. It's not really good if you wanted to kind of go into a lab and do an experiment and wanted to know, how do you do this, kind of a hands-on manual. And so I'm hoping to seriously supplement this course with that kind of practical information. If I want to run a cyclic voltammogram, what are the sorts of concerns I should have? What equipment should I be using? How do I select between different reference electrodes? Issues like that. And I'm hoping that you will ask me questions, especially on that, as we go along, because that will cue me in that I maybe haven't told you as much practical information as I ought to be. In addition to that, I will be supplementing the book with examples from inorganic chemistry, in particular the inorganic chemistry that we do at Princeton, since I happen to know that a little bit, to give you some feeling for what you can learn from using these various techniques. Now, going along with this idea that Bard and Faulkner are wonderful in the PChem, but if you want a more hands-on approach, there are better ways to do it, probably. I'd like to suggest to you two other texts. One is this book by Kissinger and Heinemann. It's hard to miss with that wonderful yellow cover. It just jumps out of the library from you. Laboratory Techniques in Electroanalytical Chemistry. It's actually an edited text. Each chapter is written by a different expert in the field. If you want to see a really fantastic chapter on photoelectrochemistry, this is the book to find it in. I can't remember who wrote it exactly. But it tells you a lot of practical things. You know, if you actually want to do a chronoamperagram, how do you set it up and go about doing it, and what are the pitfalls? And the other text along the same lines is this book by Ghigliotti. Ghigliotti actually has two textbooks. There's one called Interfacial Electrochemistry, and this one called Electrokinetics for Chemists, Chemical Engineers, and Material Scientists. This is a really wonderful hands-on text. That is, the first half of the book is very physical chemistry. In fact, much more physical than even Bard gets, worrying about the details of the interface between an electrode and an electrolyte. What are the ions doing? What is sort of happening in terms of free energy and chemical potential? If you want a lot of detail, the first half is good for that. But what's really wonderful about this book, and also the other book that Ghigliotti has out, the second half is actually the same, I believe, or very similar in the two texts, is the lab manual. And he goes through and he has, you know, a cyclic voltammetric experiment, and it's if you were going to go and do that one, it has a recipe in there for doing that, and chronoamperometry and AC techniques. And so this book is a real wonderful way if you just need to know how to do that. Now, there's a wide variety of other texts out there, and I think what I'll do next section is just hand out you a little bibliography of other books that you might want to consider. But we'll be using Bard and Faulkner. That is set up as a traditional textbook. It has problems at the end of the chapters, which brings me to the point that it's a course, and I guess I have to assign grades at some point and things like that. So there will be some problem sets, which will be a combination of the chapter problems and some of my own original ideas that will give you. I'm thinking it's going to be about every other week in terms of sort of the problem set, something like that. That will go into your grade. We will have a midterm type of exam. I'm not sure it'll be exactly in the middle, and some sort of a final exam for the course. So grades will be established. Okay, any questions on sort of administration before we get started on something more interesting? See, you're already sitting there and inhibited. No questions. Okay, electrochemistry. So let me take you back to freshman chemistry, which is hopefully the first place you saw electrochemistry, and remind you that a million years ago when you were taking your general chemistry course and you were introduced to charge transfer in electrochemistry, there was probably two things that you learned. And one of them was that you could oxidize and reduce molecules. That is, you could do electrosynthesis, essentially. So if you wanted to, for example, make chlorine, then you could take something like sodium chloride and you could oxidize that and make chlorine gas from that. And of course, you could do the reverse of that, and that's called the battery. That is, we could take something where the free energy for the reaction was going to be negative, and we could run the reaction towards the two half cells and get it out. And then the other thing, presumably, that you learned, hopefully, was that there's this thing called the Nernst equation. I say that hopefully. I'm sure you've all learned about the Nernst equation, but I remember several years ago when I was teaching a junior level inorganic chemistry course, and I said, of course, you all saw this in freshman chemistry, and they all denied ever having seen this equation before in freshman chemistry, and most of them were in my freshman chemistry course. And I remember seeing it, but the point, besides the fact that people tend to forget this, is that the Nernst equation only tells you about potential and tells you about potential under equilibrium conditions. So in freshman chemistry, there really is no current. There's just potential. There's the potential from the Nernst equation, and then there obviously has to be a current flowing when you oxidize or reduce something in an electrosynthetic cell or a battery, but it's sort of ignored. You talk about it again in terms of free energy, and that is essentially potential. So the big idea that we want to introduce in this course really is that there's current and potential and that they both interact with each other. And if you understood that in its full details, then I wouldn't have to give the rest of the course, I suppose. Because that's really all there is in electrochemistry. So if we're going to take into account current also, besides building batteries, what else are we going to be able to do? That is, up till, let's say, about mid-1950s, really, electrochemistry really was the measurement of potentials and the use of the Nernst equation. And, of course, you can get pretty far with that. You have pH electrodes and ion-selective electrodes. You can determine redox potentials for various species, and from that you can get free energies out. So that's not a trivial point. In fact, the very first measurements of activity coefficients was done electrochemically, ferrocyanide. You have wonderful ways of getting your hands on delta H's in the lab. Right? You can do bomb calorimetry and things like that, but you don't have a delta G meter anywhere in the lab. The closest thing you have to a delta G meter is a voltmeter, right? You can measure potentials, and as you know, the free energy of a reaction, the potential are directly related within a few constants, namely Faraday's constant and the number of electrons that travel in the circuit. And so if you have a reaction that's amenable to electrochemical processing, your voltmeter gives you free energy. And so up between, say, the early 1900s and 1950, that was the big deal thing. You could measure free energies and hence chemical potentials and activities with electrochemistry. It was good news also because in that time period, people knew how to build voltmeters that were extremely sensitive. We build them the same way today. It's a coil of wire. They were not very good at building amp meters. That is, if you wanted to measure an amp or so, that was okay. But if you wanted to measure even a milliamp, actually, or not to mention a microamp or a picoamp, you were in big trouble. There was not a really precise way of doing that. In fact, if you go back when electricity was first ported into houses and the electrical company decided that they needed to be charged for the amount of electricity you used, is anybody aware of exactly how that was done? How they figured out how much electricity used? This even predates me, you'll be happy to know. But there were electrolysis cells on the outside of the house, and little water in there, and they would split the water. And then, the guy who reads the meter would come around and look at the amount of gas generated over, the month. And since they knew how much electricity they were splitting off with electrolysis, that ratioed with the amount you were using. And based on the amount of gas generated, they could figure out how much electricity you used. So that you had really no good way of keeping track of numbers of electrons or rate of electrical use to start with. And it wasn't until we had things like transistors and nice integrated circuits and whatnot that you could get down to the precise measurements you needed for measuring current. So current came along a lot later, and it wasn't really until the 1950s that people started making good measurements on current. And so that aspect of electrochemistry has really lagged behind the measurement of potential. However, today we can do that, so that opens up a lot of other possibilities. The most obvious thing that it opens up is the measurement of current is a direct measurement of the rate of reaction. Faraday told us that every time an electron flows, that a redox event has taken place. It turns out it's a false statement, but it works pretty well. It worked for Faraday. We'll make a correction for that later on, maybe by the end of the hour. But that means that anytime I measure a current, if I believe Faraday, then I'm looking directly at the rate of reaction. Obviously, if I know the rate of reaction, then I can start doing the kinetics. And if I get the kinetics right, I have a good chance of getting the mechanism. Maybe a 50% chance of getting the mechanism, depending how you feel about mechanism. And so the first thing that current lets you do is look at charge transfer kinetics. Now, let's see, is everybody here an organic chemist or a physical chemist, or do I have some real-life organic chemists that are willing to take this course? No one's at least willing to identify themselves as an organic chemist. Okay, good. So when we look at, I guess, and when we look at, there's nothing wrong with organic chemistry, really, but, I of course, I tell my class that organic chemistry is a horrible thing, because as an inorganic chemist, we all realize it's the inferior science, but there's no pretty colors in it, really, a few dyes, but it is a science, yes, it is a science, but it's just not intrinsically beautiful as a science, right? However, I do have to tell you, remember that little experience over at UCLA, not too far away from here, organic chemistry, junior year, laboratory, is where I met the person who eventually became my wife. So there are some good aspects to organic chemistry. Can't totally put it down. So we will primarily be looking at inorganic examples, which I guess will suit you just fine based on your inclinations here. And there is an advantage to that. It's rather interesting that redox reactions in terms of organic chemistry go quite back in history. That is, it's a standard mechanism. You all, even if you're not organic chemists, had to take probably a sophomore year organic chemistry course. You probably have put that totally out of your mind. It was probably a life-threatening experience or something like that. And you learned all these wonderful mechanistic things, or at least you attempted to, that have wonderful names associated with them, right? And then you had these oxidation and reduction reactions. I remember from when I was learning my initial organic chemistry, there was just like a, reduce, and there was an arrow, and it said ox over it, and then there was product. Whereas all the other ones, you had a page of arrows flying to the left and the right and whatnot. I never understood why it wasn't that charge transfer reactions were just that simple, or was there something else to it? And of course, the answer is that people just don't understand, and even to this day really don't understand as well charge transfer reactions in terms of organic systems as they do in inorganic systems. And so we have all the details we would like, maybe like a few more, in terms of inorganic systems. And the main reason for that is that the big component of the free energy that one just can't ignore, whether it's organic or inorganic, in a charge transfer reaction is the so-called reorganization energy. That is what the solvent's doing immediately adjacent to the molecule when it's suddenly the molecule, maybe that's neutral, has a positive or a negative charge on it. And that could be something like half of the free energy. And if you have an inorganic system, if you have a transition metal complex, then the first salvation sphere, which takes most of the abuse when you do this, is the coordination sphere. And of course, with a transition metal complex, we can know exactly where those ligands are before and after the reaction. So we have a big leg up on handling that energy. But for some organic molecule, which just has some solvent and some organization around the molecule that's really hard to figure out, it's very, very hard to get your handle on that reorganization energy. And so mechanistically, it's a big problem. So we'll look at inorganic examples. I don't want to leave out the organic. And in fact, a couple of the textbooks that I'll suggest you might want to look at when I give you the list next hour, specifically electrochemistry for organic chemists, because you have to approach it slightly differently because of these unknowns. So we have mechanisms and we have kinetics. A big area more recently in terms of electrochemistry has been this whole area of inorganic electrochemistry, where one uses typically a measurement of potential, but sometimes current, to learn first something about a metalloprotein active site, and then secondly, in a sensor application. Can I use an enzyme, whether it's an inorganic-based system or a pure organic enzyme, can I use that enzyme to sense some specific component? And an obvious thing you might want to sense is some other biological component. A third area that has been very active, say, over the last 20 years, I was just going to say 10 years. I was forgetting how old I am, but kind of going back to when I was in graduate school, is the area of chemically modified electrodes, where we're going to go and decorate the surface of an electrode with specific molecules to change the charge transfer dynamics at that interface. So we're going to either want to shut off certain reactions, or we want to catalyze other reactions, or add some level of specificity to how the electrode interacts with some analyte in carrying this out. Also along those lines, we can slip in energy conversion. I mentioned photoelectrochemistry earlier, and certainly modifying a semiconductor surface with a molecular species has been a very important approach in the conversion of light energy to electric energy. Likewise, there's been a variety of suggestions that one might modify the electrodes of a fuel cell, for example, so that you can improve charge transfer kinetics, and we'll want to look at that a little bit and see if that makes sense or not. We'll also want to think a little bit about what we mean when we say chemically modified surfaces. That is, on the one hand, if I take, well, maybe one of my favorite pieces of material, silicon, I will slip into semiconductors, I guess, just for a second here, and I oxidize it, which is pretty easy to do by looking at it the wrong way, then I'll end up with some silicon oxide on the surface, and maybe I'll even do it carefully and end up with a silicon oxide of pretty well-established stoichiometry. And some people would say, well, that's a chemically modified electrode, and I suppose it is in some sense, in that I've changed the surface, this chemistry. On the other hand, I might go and take some nice molecule like ferrocene and attach a hydrolytically unstable silane to that and use that to anchor the ferrocene to a wide variety of surfaces. And typically when people talk about a chemically modified surface, that's what they're talking about, where I have a well-defined molecular species that has certain properties that I want to take advantage of, and I'm going to put that on the surface. So in other words, I'm taking, if you will, the interfacial or the solid-state properties of the electrode, and I'm going to endow them with some sort of molecular specificity, as opposed to the silicon oxide example that I gave you. And then finally, I should mention electrosynthesis. I mentioned that as a very old technique, but it is a new technique also in that there are a couple of species that are made electrosynthetically and not much else. It hasn't made many inroads. So my example of making chlorine actually is an old one and an industrially important one. Chloralkali process in which you get chlorine and sodium hydroxide from brine solution. Beyond that, the monomer that Monsanto utilizes for making nylon is electrosynthesized. And there's one or two other molecules, and that's it. So of all the things that you might make electrosynthetically, there's very little that really is from kind of an industrial, pragmatic point of view. And so development in that area is worth considering. Okay, so that's where we're headed. We're going to focus, again, most of our time on kinetics and mechanism this term, and then out of that, sensor applications will grow, and energy conversion applications. So let's get started. First, we need some vocabulary. Let's start off with the electrolyte. Everybody knows what an electrolyte is, hopefully, but let me point out that there's this other term, supporting electrolyte, okay, which is a little confusing. The electrolyte includes a solvent plus a salt. The supporting electrolyte is the salt that we're adding. That is, anytime we're going to do electrochemistry, we need some ions around. That's the supporting electrolyte. One would like to choose those ions, that supporting electrolyte, so it's the so-called spectator ions in the system. It's innocent, but that's not a given. And I will show you examples where things that, like sodium chloride, that you would think were just going along for the ride, in fact, are controlling the situation. So one wants to be a little bit careful in this whole supporting electrolyte discussion. Typically, from a practical point of view, we would want to get the supporting electrolyte concentration up to something like 1/10 of a molar. It's really nice. You can get away with a little bit less depending on what you're doing, and it might go all the way up to 1 molar. The other obvious thing from a pragmatic point of view to say about the supporting electrolyte is simply getting it dissolved isn't good enough. You have to get it dissociated. That is, you can take a salt like tetrabutyl ammonium perchlorate, which is a wonderful supporting electrolyte when you're doing non-aqueous work, and you can dissolve it in acetonitrile, and it'll go in at close to 1 molar concentration, and you'll have a wonderful electrolyte system. But you can also take tetrabutyl ammonium perchlorate and dissolve it in methylene chloride or benzene, close to 1 molar also. And those are not electrolyte situations because you have contact ion pairs still. You never get free ions, and nothing's happening. So just dissolving the salt isn't good enough. This brings up actually a very, very important point. When you go and you do most analytical experiments, you take an NMR or an IR or whatever your favorite spectroscopic technique is, then you can end up with a good spectrum or a bad spectrum, depending on maybe how you prepare your sample. But you will never break the spectrometer probably by preparing a bad sample. I guess you could do it intentionally, but by and large, that doesn't happen. And you can't get totally spurious data typically by preparing a bad sample, although if you work at it, I suppose you could. I see Bruce is smiling back there. Do you want to confess something, Bruce?
Just thinking about our XPS, we take lots of spectra, and there are lots of wrong answers.
Wrong answers. Well, XPS is closely related to this, I guess. I stayed away from that technique. It has electrons again. The problem with an electrochemical experiment, even worse than XPS, is that when you go and you take your electrochemical cell and you attach it to a potentiostat, it becomes an active element in the electrical circuit of the potentiostat. And so depending how you prepare your sample, your electrochemical cell, you can get all sorts of artifactual answers, and you can break the potentiostat for that matter in doing this. So it's not such an innocent experiment anymore where, okay, I'm going to go and run a spectrum and see if it's a good sample. And there have been more papers than certainly I can count that have been published in the literature where somebody has seen this wonderful signal and they've interpreted it in terms of this wonderful theory that has a molecular basis. And in fact, what they were seeing had nothing to do with what the molecules per se were doing in their electrochemical cell, but simply the fact that you have resistors and capacitors in your potentiostat. Your cell, for all intents and purposes, looks like a series of resistors and capacitors, and they had simply inadvertently modified their circuitry. Okay, if you went into an NMR or even an XPS and you tore out the electronic guts and put in your own motherboard, then you might guess that things would change. And what you need to remember when you're doing an electrochemical experiment is every time you connect your cell up, that's what you're doing. So one has to wonder whether what you observe is actually a molecular phenomena or is something else. And the supporting electrolyte issue is a very good example because I can make the resistance of my electrochemical cell exceptionally large either by forgetting to put in the supporting electrolyte or utilizing a solvent where I'm not getting much dissociation. Okay, I can fool myself. Yes?
Can the amount of electrolyte that you put in there, can Can I shift your solvent windows at all?
Oh, absolutely. Yeah, shift your solvent windows, shift your capacitance, I haven't mentioned yet, as well as your resistance. But sometimes the electrolyte, I said you would like something that's innocent and it's just spectator ions, but if you're going for a big solvent window, often you can hit the potentials where you're going to oxidize or reduce the supporting electrolyte. Okay. In effect, it's also this capacitance, which may shift your window some also. Okay. When you shift your resistance and your capacitance, then you shift the RC time constant for your cell, so your whole system response may change dramatically when you do this. So there's almost nothing in the electrochemical cell that you can't mess up by messing up the supporting electrolyte. So one wants to think about that very, very carefully. And that, of course, is going to change. The other aspect of the supporting electrolyte is one often can run into a situation where there is either phys or chemisorption of materials on the electrode, and that would be sort of an unintentional chemically modified electrode. It might be the supporting electrolyte ions that chemisorb, physisorb. That could be an issue. But you can also have various salting in and salting out effects that will deposit some other species upon addition of the supporting electrolyte on your electrode. And so you have these second-order effects that can be an equally big problem. Okay, so we'll come back to that discussion a little later, but that's a big one up front. The supporting electrolyte is a critical issue. Okay, then in addition to that, of course, you need to have some electrodes. And it's probably more obvious that the electrode materials that you pick will affect the electrochemical response of the cell. For all, not all, for a lot of the experiments we'll be talking about this term, we're going to want to use a potentiostat, where we're focusing our potential control on one electrode and letting the other electrode do whatever it wants to, as long as it doesn't get in the way. And the problem with that is, how do you know when that second electrode is getting in the way or not? That is, if suddenly it becomes the controlling factor, then you're watching this auxiliary or counter electrode instead of the electrode that you're trying to control. And one way that it can become a factor is if its area is small compared to the area of the working electrode, the electrode that you're trying to focus on. Okay, so I've just thrown in a whole bunch of words here that maybe I should clarify. So we have our working electrode. That's going to be the electrode that has potential control. And something really important to recall, it depends who you buy your potentiostat from, but many of the manufacturers actually put the working electrode at ground, which may sound counterintuitive, but this is fine. You can still have potential control. This becomes really important if you're hooking up other equipment to your electrochemical cell. It's nice to know where your ground is or isn't. And as I said, it does depend on exactly what potentiostat you purchase. So it's important to know which side of the cell is grounded, but often it is the working electrode side that is the grounded side. You actually have more control that way. Then you're going to have either what's called an auxiliary electrode or a counter electrode. And as I was saying, you don't want that electrode to become limiting in any way. And the easiest way to have that become a limitation is make the area of this electrode small compared to the area of the working electrode. Okay. The important consideration here is current density. And so obviously, if I'm passing an amp through my working electrode, then I'm also passing an amp through my counter electrode. But if my working electrode is on the order of, say, 1 square centimeter, then my current density there is an amp per square centimeter. And if my counter electrode, say, is on the order of a square micron, then I'm passing 1,000,000 amps per square centimeter. And obviously, that's not going to happen. And so things are going to happen on this side. And I no longer have a system where I'm controlling this electrode and letting this one just respond. So the area here is critical. We need large area. Now, the other way you could fool yourself on the counter electrode is you could pick a material for your counter electrode which is kinetically sluggish. So even though you have a large area, the rate you can push electrons through it is slow. And again, that can become the controlling factor. So typically for the counter electrode, people would use platinum. nice catalytic interface, and then all you have to be concerned about is that the area of that counter electrode is large compared to the working electrode. The geometry of the counter electrode isn't too critical at all. The geometry of the working electrode, it turns out, is quite critical. So one can take, for example, a spiral of platinum wire or a sheet of platinum. Wire is a little less expensive, and that makes a great electrode for the counter electrode. And then finally, the third thing that we're going to want in this system isn't an electrode at all. We won't always use it, but for many of the experiments, we're going to want 3 electrode cell, and so we're going to have a reference electrode. And I'll just either remind you or state you that a reference electrode is not an electrode, it's a full half cell. And again, that's worth remembering. That is, there's more than just a piece of metal that can go wrong with a reference electrode, since it's a half cell there. And again, you want to think about how that reference electrode is interfacing with the rest of the cell. That's another area where you can get all kinds of wonderful artifactual results. Next piece of nomenclature that we have to clarify is this whole idea of whether a current is a positive current or a negative current, which, thanks to, I guess, a historical argument between chemistry and physics, is never clear. And in fact, it's worse than that. It's a historical argument, I guess, between chemistry and chemistry also. So, for example, if you, because it not only affects current, but also potential. So we'll start off with potential issue there. They go together. If you pick up a text or a journal article that was written prior to 1970, that has to do with chemistry, or if you pick up a text or a journal article written after 1970 by somebody who was practicing electrochemistry prior to 1970, then you will find that things that have to do with oxidation are assigned a negative sign in general, and things that have to do with reduction are assigned a positive sign. So there's a very famous book, which is a listing of redox potentials put up by Latimer, and I think this is in the right around 1960. And so if it was an oxidation, he assigned that a positive potential. 1970, IUPAC decided that they were going to have some rules about exactly how you do your signage in electrochemistry, and it turned out that internationally it was agreed that cathodic reactions would be associated with a negative sign and anodic reactions with a positive sign. So if you learned electrochemistry after 1970, then you're dealing with a situation where we have potential going positive to the right and negative to the left, and current going positive and negative. And so things that are happening up here are oxidations, and things that are happening down here are reductions. And if you're using the convention that was in place prior to 1970, then just go to the other side of the board and flip this over. You'll be in great shape. It's the mirror image. Okay. And the key problem with this, and I actually have to give Al Bard a lot of credit for this, both the good and the bad, actually. This older convention, in fact, has become known as the Texas Convention because Bard and Faulkner at the University of Texas. And basically, when IUPAC came out with that, they said, fine, but we've always done it the other way, and why should we change? And so if you look at all their journal articles, they use the Texas Convention, not the IUPAC Convention, and it's the mirror image. But when they went and wrote their textbook, which was much more recently, they did use the IUPAC Convention in here. So if you go and say, OK, I understand what they're saying in here, and I'm going to go pull some of their journal articles, now you can get yourself totally confused. So beware of that. Figure out which convention is being used on that. Now, in terms of energy, which is the other thing we like to relate this to, typically if we're doing some kind of energy argument, we like energy going up to be higher energy. And again, we have this relationship where we are going to relate our free energy of reaction to minus n Faraday's constant delta E. And so you see there's a flip-in sign that's going to occur here. So when we're going higher in energy, if we want to compare that to a potential scale, we need to put energy that's higher as negative and energy that's lower as positive. This was all done just to make life confusing for all of us. It's not that it's hard enough to start with. Okay, so if you want to measure energy, for example, in electron volts, which is particularly easy if you'd like to compare that to a potential scale where we're working in volts, then just remember that more negative electron volts is a more negative potential. That works fine, but it's higher in energy. That is, if I'm on this scale here and I find out molecule doesn't reduce until I get way out here, I'm using more energy to reduce it than if it reduced at a more modest potential, less negative potential. So the IUPAC and the energy scheme do go together. So a simple way we could put this together then would simply say we have an electrode here, right there. On this side, we have an electrolyte. On this side, we have the electrode. Assuming the electrode is made out of a metal, then I can apply a potential to that metal, and that potential will control where the Fermi level of the metal is, highest occupied molecular orbital, if you will, of the metal. Is Fermi level a term that you're all familiar with? No problems? Good. So I have a bunch of filled states below that, a bunch of empty states above that. Of course, I get to move that around by applying a potential back here. Out in the electrolyte, I have some molecule that has highest occupied orbital and an unoccupied orbital. And the simple argument is that if I am energetically at a potential where electrons can flow into an empty orbital, which can't happen right here, then a charge transfer will take place. So that's not possible because I have totally filled states here. So I'm going to have to move my Fermi level positive in order for that to occur. That's the oxidation. Right? On the other hand, if I want to populate this molecule out here with an electron, obviously the first orbital I could put an electron in is something up here. And again, that's going to require an electron over here of similar energy or higher energy, and I have nothing over here, so there's no way I can do that right now. But if I move my Fermi level more negative, then I will populate the states below it, and I can get the reduction to occur. So this IUPAC formalism and this concept of energy flow work together. Okay, now we can go. That's nomenclature. We're doing great here. Now we can go and we can divide the world down into essentially two types of experiments that we can do electrochemically. We get to control the potential or control the current. We don't get to do both at the same time. Right? One of those is a dependent variable. The other is an independent variable. If you look back at the earliest electrochemistry experiments, once people were starting to flow current, 1950s, even 1960, the initial experiments that were most favorable were those in which you controlled the current. And again, that was because measuring current was problematic. You couldn't do it to the extent you wanted, and so you could set a current, and then you could measure potential. And so a so-called chronopotentiometric experiment is sort of the first, historically, of the modern electrochemical experiments where you're setting a constant current using a galvanostat and watching a flow of current as monitored by a change in potential. So experimentally, it's the easiest experiment to do in terms of interpreting the results. It's one of the hardest experiments to do. And so once people could get a handle on measuring current, then you came up with a set of potential controlled experiments in which current was the parameter of interest. Now, in doing this, I have a colleague. My biggest research effort right now at Princeton is in the area of fuel cells. And in order to do a fuel cell is a really strange thing in that chemists only understand about half of fuel cells, what a fuel cell does, and engineers understand only about half, and they're the opposite halves. And so you really have to work with an engineer in order to make a fuel cell work right. One of the reasons is a fuel cell does not have a reference electrode in it, and introduces all kinds of interesting engineering complications as a result. There are other interesting engineering complications besides the reference electrode. Anyhow, a lot of fuel cell research has been done by electrochemists as opposed to chemical engineers. And electrochemists think more or less the way I've been telling you to think for the last 45 minutes. That is, in terms of potential and current, and in terms of this sort of thinking, in a 3-electrode type of cell. Engineers don't think about 3-electrode cells to any large extent. They might, but what they're interested in is making something that could be used to put energy into something else. Fuel cell, for example. And so when you're running a fuel cell, what are you doing? You're generating some current and some potential, and you're running it through an external load. Simplest one, say, being just a simple resistor. Okay. And so the question is, when you're doing that, which parameter are you controlling? And I promise you, if you go out on Colorado Boulevard and find some electrochemists and ask them, they'll tell you that really you're controlling potential if you do that, and the current's doing whatever it wants to do. But in fact, that's really not true. You're controlling resistance when you do that, and the current and potential are allowed to do whatever one wants to do. That is, when you're using a potentiostat, you have designed a system very specifically that lets you control potential and monitor current. If you're not using a potentiostat, if you're just using a load, then you're controlling neither. Even though they're two linked parameters, you're not controlling either one. You're simply controlling cell resistance. So if you want to build a fuel cell, that's say going to run a car or something like that, you don't want to look at it as a system that is a potential control experiment that's generating a current that's going to run the electric motors in your car. You want to look at the car as a load, and you want to ask yourself, how does the load impact the fuel cell performance? We'll get to that, but we'll throw that out right in front. That what I've had to say here only applies to potentiostated circuits. Okay, so assuming we're potentiostated and that we're going to monitor current, and we're using a 3-electrode cell with our potentiostat, so that we're working under the conditions, the very specific conditions that I've laid out here, then what sorts of experiments can we carry out? Let's start over fresh here. So let me shoot up on the board over here an outline of what's possible. Well, my machine has been sleeping too long there. Okay. So we're going to do a potential control experiment. Is this, can you guys in the back see this? This is like an eye exam, right? No, we're okay. We've got great eyesight on this side. How about on that side? Okay, sort of. So I'm going to go over this, and I think I'll use the board also. But I've divided the world into two things. We can do a static potential experiment. We just pick a potential, and we're going to stay there. End of story. And we're not going to even look at what's happening in this cell immediately after we pick it. We'll let everything come into steady state, and then we'll consider what's happening. Or we can dynamically change our potential. So that's what's on the right-hand side of the chart over there. And I'd say, again, this is sort of historically the early experiment, the static potential experiments, kind of 1950s and more recent. And in dynamic experiments, where we're actually changing the potential, it's just starting in the 1950s and then coming up to today. Okay, so just really reviewing what I've already told you in terms of the static experiment, the classic static experiment would be an experiment where I am in thermodynamic equilibrium. And obviously, by definition of equilibrium, that means that the current I here has to be 0. We don't have a process occurring, so we have no rate for process occurring. So we have 0 current there. And again, that would lead us to something like the Nernst equation over here. Right, so that I'd have an equilibrium potential, just to remind you here, that is related to a standard redox potential plus a term that takes into account our concentration of reduced species. Oops. There we go. Reduced over a concentration of oxidized. And let me just remind you, when Nernst wrote this down originally, He didn't use a natural logarithm. He used a base 10 log, so you have to throw in a factor of 2.3. Logarithm of red over ox. So instead of writing concentration and whatnot down all the time, I'm going to talk about reduced over oxidized as red over ox for the rest of the term, and take you back to that discussion we had a couple minutes ago about IUPAC. In making that sign convention, what they were essentially saying is that the standard way you will write out all reactions, all half reaction, is as a reduction reaction. So again, if you go back to Latimer's book, then all the half-cell reactions are oxidation reactions in Latimer's book. If you go more recently, Bard and Parsons put out a more up-to-date compilation of redox potentials, a wonderful book that has just about every redox potential you could think of in the world in it. And they've written everything as reductions. So our generic reaction is that one right there. If we are operating at room temperature, then this term right here is 59 millivolts divided by n, the number of electrons that transfers. And so you can see we obviously have a way now of relating potentials to concentrations, and a very powerful analytical way. That's our pH electrode, essentially, our ion selective electrode. And that's all done under an equilibrium, sort of, or pseudo-equilibrium condition. On the other hand, holding the potential static doesn't mean that current doesn't have to flow. That is, when we do a measurement like this, we use a high impedance system to ensure that current doesn't flow. But we can let current flow in these systems. Obviously, the Nernst equation isn't going to apply then. And then when we have current flowing, we have two options. We can have very fast charge transfer kinetics. If we have that situation, even though we're not in a static equilibrium, we are approaching something that is close to equilibrium at the electrode-electrolyte interface, and going back to a Nernstian condition is very reasonable. Okay. On the other hand, we may have slower kinetics where the rate of charge transfer is the rate-limiting step in our reaction, and then we have to develop some sort of a kinetic scheme that allows us to follow that. And initially, this was worked out by a gentleman by the name of Tafel. This was an empirical equation, the Tafel equation, that described the relationship between a potential and a current. And then a more detailed physical-chemical understanding of that equation was provided by Butler and Vollmer, relating it back to concentrations and rates of reactions and things like that. So we will look at that. That's basically what we have possible in terms of a static experiment. If we're going to change our potential, then we have two situations also. One I've already mentioned is we can have a Ferdaic reaction. That is a reaction where what we have over here is happening. An electron flows through the circuit, and something gets oxidized or reduced. Question?
For the dynamic potential?
Yeah.
You just mean constant current?
No. No, these are all potential controlled experiments. So the question is, yeah, when I say dynamic potential, am I controlling the current? No, I'm dynamically controlling the potential. So I'm doing something like a cyclic voltammogram or a chronoamperogram where I'm slewing my potential or jumping my potential. These are all potential controlled. And the simplest experiment would be a potential jump, a chronoamperogram, for example. And I could sort of zeroth order say what I expect there then is that I'll end up with something that Faraday's law describes. That is, I oxidize, well, if it was Faraday, it was silver. I oxidize silver to silver ions, and every time I see one electron in the external circuit, I end up with one redox event that's occurred. Okay? This, by the way, that silver experiment is the genesis of the Coulomb, right? That is, at the point the Coulomb, the fundamental unit of electrons, was defined, we didn't quite understand moles and coulombs were somehow related, unfortunately. As a physicist, Faraday was a physicist that day, I guess, was doing his Coulomb experiment, and Faraday on a different day was doing mole experiments, but there wasn't an understanding of what was happening there, so they needed a fundamental unit. And he knew that he could do something like reduce a gram of silver, which was the basis for this, and he could very precisely weigh the amount of silver that he had. And so he said the amount of electricity it takes to reduce a gram of silver ions to silver metal we'll define as the fundamental unit. There's your Coulomb. And that's why we're stuck with Faraday's constant in here today. By the way, that is a script F, the way I write it, because last term when I was teaching this course, 3 weeks into the course, a student came up to me and said, "What is this?" It's just an F. And of course, that's just the ratio of coulombs to moles, which turns out to be, if you like, sort of zero significant figures, 10 to the fifth. 96,496, if you like a few more significant figures. So on the one hand, we can say that's happening. On the other hand, what Faraday sort of didn't understand was the first thing that happens when you pass charge through an interface is that you get rid of some entropy at the interface. That is, if I have an electrode, there's case 1, case 2, if I have an electrode sitting in solution again, there's my electrode, there's my electrolyte. If I suddenly go and dump, say, some electrons on this interface, I have a bunch of negative charge there. And this electrolyte, which is out here, which has supporting electrolyte in it, as well as dipoles that are associated with the actual solution molecules, is going to respond to that. And so obviously I'm going to bring up things like cations to that interface. Or perhaps if I'm using, say, water as my solvent, I have a nice dipole moment, I might be arranging my solvent dipoles, something like that. And of course, as soon as I do that, the rest of the solution is going to look at that and not be happy with that. It's going to see a wall of positive charge there, and it's going to bring up negative charge to balance that out, or potentially some dipole moments that go in the other direction. And that will keep going until eventually fuzzes out, and I'm way out here in bulk solution, and I have just a random assortment of charges again. Okay. Now, that's work, and work takes energy. We have to get that energy from somewhere, and where are we going to do it? There's going to be a flow of electrons associated with this. So we have non-Faradaic processes. And it's just the organization of this interface when we apply a charge to it. And Faraday missed this whole thing because for some reason his, I don't know, his laptop computer really couldn't see things happening on a millisecond time scale. Given that I think his stopwatch actually was probably a thing with sand in it, right? So he didn't see that. But now that we can look on a millisecond or a shorter time scale, we find that this whole organizational process dominates the early time charge transfer chemistry. And so we have these non-Faradaic processes. And one either has to say, I'm not really interested in that. I'm interested in the Faradaic part. And so I will do things to minimize this aspect so it doesn't confuse me. Or one might say, well, I'm building this whole organization at the interface. Can I use that to interrogate the nature of the interface? So I might actually use the non-Faradaic component as a way of studying the interface. Take it either way. Okay, so we have those two possibilities going on there. If we want to minimize this, because we're really not interested in it, we can never make it go away, but we can minimize it. There's two things that we can do. The first is, again, what I said earlier. If we have a lot of supporting electrolyte around, then you see we don't have to do as much work to bring these things up, and so we can minimize the amount of energy that's needed to do that, and that will help quite a bit. This is also, by the way, the reason that you never do electrochemistry without supporting electrolyte around. If all you're going to rely on is the dipole, say, of distilled water to do all of this, it's going to take a tremendous amount of energy, much of which will be released as heat, to do it. So you'll have, A, you'll have a lot of heat generated, and B, it's going to be very sluggish type of thing. So you'll never see the nice, beautiful electrochemistry you want to see. You'll just see this organizational thing going Another way we might do this is simply say, okay, for the conditions that we're operating under, we know that it's going to take 4 milliseconds for the interface to organize itself, and so we'll just look later in time than that. Or we know for the first 4 milliseconds there's something going on here, and so we will somehow deconvolute that process because we want to look in that 4 millisecond time window. Now, if we want to do that, then you simply have to realize that that interface, for all intents and purposes, looks like a parallel plate capacitor. Okay. And so we could describe this process of building up this so-called double layer as the charging of and discharging of a parallel plate capacitor. And so the first thing that would pop into mind is that we're going to have an exponential drop-off in the current associated with this that's dependent on an RC time constant. Again, the R will depend on exactly how much supporting electrolyte is out here in the bulk, because that can be your major resistance. The C will depend on exactly what you have available to organize that double layer. Those of you who are more familiar with semiconductors, then you have a space charge layer in a semiconductor on this side, and it is the mirror image of what's happening out here. They are identical. Okay, so if you understand space charge layers, you already understand the double layer. If you don't, you understand neither, I guess, but we'll get back to that in a couple minutes. Okay, so we have a non-Faradeyic response. We have a Faradeyic response. If we're doing a Faradeyic response, then we can talk about kinetics again, and we can divide the world down into fast and slow charge transfer kinetics through the interface. And as I said before, if it's fast, then at the interface, even though we are not officially in equilibrium, obviously, because current is flowing, we're going to have a situation, since the rate-limiting step is not the charge transfer itself, that the Nernst equation applies. That'll be a pseudo-equilibrium situation that we could use to define what the interface looks like. What will presumably be limiting, and what typically is limiting when we have fast charge transfer kinetics, then, is bringing up molecules from out in solution to be oxidized or reduced at this interface. And typically, we would set up a situation where that's a diffusion-controlled process. More generally, we can say it's certainly a mass transport-controlled process. Okay, so by taking the Nernst equation as a boundary condition along with whatever mass transport we're using, then we define what's happening in terms of a fast charge transfer reaction. If it's a slow charge transfer reaction, then obviously we're never in an equilibrium situation. That is, I'm talking about the heterogeneous charge transfer of electrons across the semiconductor electrolyte interface. And now we need some sort of a kinetic statement, such as Butler-Volmer, that will define what's happening there. So when we're fast, we're Nernstian plus mass transfer control. And when we're slow, it's charge transfer kinetics. Okay. Doing okay? Everybody's hanging in there? Okay, so let's start off with, since this non-Faradeyic business has to occur whether we have a Faradeyic process or not, let's look at that. Yeah, so we understand what it can do for us or what it can do to us. Let me just show you, in terms of some experimental data, what I'm talking about here. This actually, there's two purposes for this. First one is, I actually took this data, so you should be really impressed that I can use an oscilloscope. And it was sort of circa 1980. It was at Princeton already, though. So, but we didn't really have computers yet, so it's just Polaroid on the oscilloscope. Wonderful old technology. Look at that. Even today, you know, I haven't inadvertently had a gamma ray come through here and erase my data. Never lost it. The second is what I have here. This is an acetonitrile electrolyte, so fairly high resistance. I have tetrabutyl ammonium perchlorate in there as a supporting electrolyte. My box here is a 2 millisecond box with a 1 milliamp full scale. And I'm doing a potential step experiment here, a chronoamperometric experiment. And so I start down here, and I jump up here, and I get this response. As you can see, in this system, I have a a millimolar of ferrocene in solution. So I'm looking at the oxidation of the ferrocene. Experiment down here, exactly the same experiment with the same electrodes. Nothing has changed. This potential jump happens to be a 0.6 volt jump. I'm doing a 0.6 volt jump down here. The only difference is I didn't put the ferrocene into the cell. And there's your current response. Okay. And you can see just qualitatively, they're different. Exactly the same cell. In fact, it really is exactly the same cell because I didn't do it the way I just told you I did it. What I did over here is I jumped through a 600 millivolt window where I knew ferrocene would go from its reduced state to its oxidized state. And over here, I jumped through the same 600 millivolt window, but I picked a region where ferrocene was going to stay in its reduced state, that there was not going to be any charge transfer chemistry. So I was certain whatever interesting structure I had at the interface didn't change because I changed the electrolyte or anything like that, and yet you get this very different response. What probably you can't tell for certain by eye is that is an exponential decrease in the current right there. In fact, you can take that curve and you can back out that I have 85 ohms of resistance there and a capacitance that's about 2.3 microfarads. If you need a ballpark number for just about any metal electrode, it's about 20 microfarads per square centimeter of electrode. It's about a tenth of a square centimeter that I have there, so it works right. So if you, great rule of thumb, if you just need to have a guess at the RC time constant, 20 microfarads per square centimeter. And in this particular cell, I get a RC time constant of 0.2 milliseconds when I carry out that experiment. And I've really loaded that cell up with supporting electrolytes. So that's about as good as you can do in a non-aqueous electrolyte. And it'd be a good idea if you really wanted to study a current that had to do with a Faraday process. You might go 3 time constants beyond that to make sure that you're really down there. So again, it's 2 milliseconds per box here. And so if I go from this point, if I go out 3 boxes, so I have a little over 2 millisecond lifetime, I'm over there, and you can see my current is essentially negligible at that point. So if I were to wait in this particular case to 2 milliseconds to 6 milliseconds, I can be very certain that any current I saw at that point was going to be from a Faradaic process. And you'll notice when I have the ferrocene around, where I have a very different shape, and probably by eye you can't tell that is a tiny minus 1/2 response, but if you go plot it out, that's what it'll work out to be. You can see if I go out a similar distance, 3 boxes out here, that although I'm missing a big chunk of current, there's a lot of current over here. My zero's down here. So I have quite a bit of current out here to play with still. Okay. So 2 choices, assuming I'm not going to change the chemical composition of the cell. Either I go out some distance like that, and you can decide maybe you don't want to go out 3 constants. Maybe you're happy with a little bit of an error in here and only want to go out 2 constants or 1 constant, and just pick off the points out here. Or you can try and deconvolute these 2 curves, which is pretty challenging, it turns out. If you needed time, that was going to be, say, within the first couple milliseconds. You have 2 problems here. First, if you want to go a very short time, you've actually lost potential control. It goes off scale here, and it's not because I've misset the oscilloscope. It's going off scale because you lose potential control in the very earliest time period, and you have to wait for the potentiostat to get back and reestablish the potential that you're dealing with. But in addition to that, even if you go beyond that, you're looking at a subtraction of 2 very large numbers to come up with a small number, and the chances of doing that successfully are pretty limited. So you'd have to have an exceptionally good data set in order to do that deconvolution. Now the other way, by the way, to make this whole thing faster, if you need to, is to have a smaller current flowing. Okay, if we limit our current. And the way we might do that is, since the current is proportional to the area of the electrode, if we use smaller electrodes, then we can limit it. So one can go, for example, down to ultra-micro electrodes. These would be electrodes that, say, if we were looking at a circular electrode, would have a diameter of 10 microns or less. Kind of 10 microns is sort of the official cutoff point for an ultra-micro electrode. and we get a lot less current flowing through the system. We'd be talking about picoamps of current, and much faster charge transfer process could be followed as a result of just that small current. Also, by having this smaller area, our RC time constant is dropping way down because the capacitance, remember, is 20 microfarads per square centimeter. And if I drop down to a minor fraction of a square centimeter, then RC is wonderful. Okay, so that's what we're talking about from a very physical point of view. Now, what's actually happening here when I go and do this? And grossly, this is what's happening. But of course, that graph right there doesn't tell us anything about what the ions are doing. It tells us that we have a complex current potential relationship that's involved there. So once this thing is set up, what do I have? That is, when I'm out here because I've developed this whole structure in here, and it's there now. That double layer is there. And so exactly what do I have? And I will just tell you, we can divide that double layer into two regions. Now let's divide it, the double layer into two regions. But let me go out here and remind you that there is a bulk electrolyte out there with random ions and solvent around. And that we have this double layer structure. And that double layer structure is going to have a region in it right adjacent to the electrode where we have a lot of ions and a lot of organized solvent. And that's called the compact double layer. And often this plane here is referred to as the inner Helmholtz plane. And that typically is about what I've drawn there. It's about 2 molecular layers thick. You have a lot of organization in the first 2 molecular layers. Then after that, you get into this region where you have some organization, but not really like I've shown you there. And that is the diffuse double layer. And then that goes out to the outer Helmholtz plane, at which point we arbitrarily say we have bulk solution. If I was to look at that now, not in terms of where the ions are, but in terms of the potential, if I'm measuring potential versus distance, then what I'm telling you is I start off right at the electrode at 0, and I've applied some potential, or the electrode has established some potential phi, and that's what it is. Somehow it's established. And then let me call that phi sub m, s. In fact, you know what I'd like to do, actually? Let me reverse this whole thing. Let me put my metal potential down here. That is my electrode potential right down here. And then when I get way far away from the electrode out in solution, there's some potential associated with the solution. So phi sub s up there. So I'm going to start over here. I'm going to end up, or rather, I'm going to start over here. So I'm going to end up over here. And that potential drop has to occur through this double layer. So I'm going to get a very steep potential drop. That's going to take me to the through the inner Helmholtz plane, IHP, inner Helmholtz plane, and then a smoother drop off in potential until I get out here to the outer Helmholtz plane, OHP. So I'm dropping a huge potential across that double layer. Yes?
What's the subscript on the lower?
This is an M for metal. Okay, potential of the metal, potential of the solution. And I'm going to have to apologize in that I'm not used to quite such small board space, and things are getting congested there. Pardon?
The IHP is the
The IHP, the inner Helmholtz plane right here. Right, so you're dropping a large amount of potential there. You drop a lot of potential over a short distance. You're dropping quite a bit of potential here also, but over a larger distance. And again, exactly what those numbers are depends on exactly what your solvent is, what your supporting electrolyte is. But this is, these are fairly large numbers. So for example, there was an experiment that was first done in the early 1980s where carbon monoxide was chemisorbed onto a platinum electrode in an electrochemical cell. And the IR spectrum, the CO, was observed, and as a function of the electrode potential. So we're not doing any charge transfer chemistry. CO is just sitting there, and what it's experiencing is whatever's happening out here in terms of all this organization. And what you observe is as you change the electrode potential away from the so-called point of zero charge, as there is some potential on this electrode where this potential and this potential happen to be the same. And if I find that, then there is no potential drop across this thing. So we have, and therefore there are no ions, in other words, that are generating an ion gradient out here. So that's the point of zero charge. I have nothing ionically physisorbed onto that surface. So if I can find that point, presumably the CO is just like a CO bound to a platinum in a platinum complex. And then as I apply a potential, I'm doing all this stuff, move away from the point of zero charge. And one observes experimentally that the vibrational frequency of the CO shifts. So the question, is actually somewhat debated now, but not as much, is, was that shift due to the fact that I had this huge electric field here? Is this a Stark effect spectrum where I've taken CO, and if I taken CO and I put it, you know, across two plates in a Bruce-type experiment, actually, right? I'd see shifts in CO as I apply a big electric field to that system. So am I doing that? Or is this an effect that's due to the pi back bonding of the CO? That is, as I change the potential on the electrode, not only am I doing all of this stuff, but again, I'm moving the Fermi level of the electrode around. And so I may be pushing electron density into the pi star orbital of the CO and changing the bond order of the CO. So there's a huge debate about this to start with. Actually, initially there wasn't a huge debate because it was a bunch of inorganic chemists. They said, oh, obviously it's back bonding, and you're changing the bond order of the CO because that's what inorganic chemists think about. And then other people came along and said, well, this is a possibility also. And you know, the truth is some of both, actually. That's what's going on there. So, but this is a big effect. You can subject a molecule to a field of 1,000,000 volts per centimeter at an interface. It's a non-trivial thing. Okay, it looks to me like this is a good point to stop at, wrap things up. We will continue then next Tuesday. We'll pick it up from the non-Faraday current and work our way into a Faradaic response. Like cell or battery, but it's sort of ignored. You talk about it again in terms of free energy, and that is essentially potential. So the big idea that we want to introduce in this course really is that there's current and potential and that they both interact with each other. And if you understood that in its full details, then I wouldn't have to give the rest of the course, I suppose. Because that's really all there is in electrochemistry. So if we're going to take into account current also, besides building batteries, what else are we going to be able to do? That is, up till, let's say, about mid-1950s, really, electrochemistry really was the measurement of potentials and the use of the Nernst equation. And, of course, you can get pretty far with that. You have pH electrodes and ion-selective electrodes. You can determine redox potentials for various species, and from that you can get free energies out. So that's not a trivial point. In fact, the very first measurements of activity coefficients was done electrochemically, ferrocyanide. You know, you have wonderful ways of getting your hands on delta H's in the lab. Right? You can do bomb calorimetry and things like that, but you don't have a delta G meter anywhere in the lab. The closest thing you have to a delta G meter is a voltmeter, right? You can measure potentials, and as you know, the free energy of a reaction, the potential are directly related within a few constants, namely Faraday's constant and the number of electrons that travel in the circuit. And so if you have a reaction that's amenable to electrochemical processing, your voltmeter gives you free energy. And so up between, say, the early 1900s and 1950, that was the big deal thing. You could measure free energies and hence chemical potentials and activities with electrochemistry. It was good news also because in that time period, people knew how to build voltmeters that were chemistry. So let me take you back to freshman chemistry, which is hopefully the first place you saw electrochemistry. And remind you that a million years ago when you were taking your general chemistry course and you were introduced to charge transfer and electrochemistry, there was probably two things that you learned. And one of them was that you could oxidize and reduce molecules. That is, you could do electrosynthesis, essentially. So if you wanted to, for example, make chlorine, then you could take something like sodium chloride and you could oxidize that and make chlorine gas from that. And of course, you could do the reverse of that, and that's called the battery. That is, we could take something where the free energy for the reaction was going to be negative, and we could run the reaction towards the two half cells and get it out. And then the other thing, presumably, that you learned, hopefully, was there's this thing called the Nernst equation. I say that hopefully. I'm sure you've all learned about the Nernst equation, but I remember several years ago when I was teaching a junior level inorganic chemistry course, and I said, of course, you all saw this in freshman chemistry, and they all denied ever having seen this equation before in freshman chemistry, and most of them were in my freshman chemistry course. And I remember seeing it, but the point, besides the fact that people tend to forget this, is that the Nernst equation only tells you about potential and tells you about potential under equilibrium conditions. So in freshman chemistry, there really is no current. There's just potential. There's the potential from the Nernst equation, and then there obviously has to be a current flowing when you oxidize or reduce something in an electrosynthetic manual. And so I'm hoping to seriously supplement this course with that kind of practical information. If I want to run a cyclic voltammogram, what are the sorts of concerns I should have? What equipment should I be using? How do I select between different reference electrodes? Issues like that. And I'm hoping that you will ask me questions, especially on that, as we go along, because that will cue me in that I maybe haven't told you as much practical information as I ought to be. In addition to that, I will be supplementing the book with examples from inorganic chemistry, in particular the inorganic chemistry that we do at Princeton, since I happen to know that a little bit, to give you some feeling for what you can learn from using these various techniques. Now, going along with this idea that Bard and Faulkner are wonderful on the PChem, but if you want a more hands-on approach, there are better ways to do it, probably. I'd like to suggest to you two other texts. One is this book by Kissinger and Heinemann. It's hard to miss with that wonderful yellow cover. It just jumps out of the library from you, Laboratory Techniques in Electroanalytical Chemistry. It's actually an edited text. Each chapter is written by a different expert in the field. If you want to see a really fantastic chapter on photoelectrochemistry, this is the book to find it in. I can't remember who wrote it exactly. But it tells you a lot of practical things. You know, if you actually want to do a chronoamperagram, how do you set it up and go about doing it, and what are the pitfalls? And the other text along the same lines is this book by Gigliotti. Gigliotti actually has two textbooks. There's one called Interfacial Electrochemistry, and this one called Electrokinetics for Chemists, Chemical Engineers, and Material Scientists. This is a really wonderful hands-on text. That is, the first half of the book is very physical chemistry. In fact, much more physical than even Bard gets, worrying about the details of the interface between an electrode and an electrolyte. What are the ions doing? What is sort of happening in terms of free energy and chemical potential? If you want a lot of detail, the first half is good for that. But what's really wonderful about this book, and also the other book that Gigliotti has out, the second half is actually the same, I believe, or very similar in the two texts, is the lab manual. And he goes through and he has, you know, a cyclic voltammetric experiment, and it's if you were going to go and do that one, it has a recipe in there for doing that, and chronoamperometry and AC techniques. And so this book is a real wonderful way if you just need to know how to do that. Now, there's a wide variety of other texts out there, and I think what I'll do next section is just hand out you a little bibliography of other books that you might want to consider. But we'll be using Bard and Faulkner. That is set up as a traditional textbook. It has problems at the end of the chapters, which brings me to the point that it's it's a course, and I guess I have to assign grades at some point and things like that. So there will be some problem sets, which will be a combination of the chapter problems and some of my own original ideas that will give you. I'm thinking it's going to be about every other week in terms of sort of the problem set, something like that. That will go into your grade. We will have a midterm type of exam. I'm not sure it'll be exactly in the middle, and some sort of a final exam for the course. So grades will be established. Okay, any questions on sort of administration before we get started on something more interesting? See, you're already sitting there and inhibited. No questions. Okay, Electrode. So my name is Andy Bocarsley. I'm teaching this course on electrochemistry, and I'm a professor of chemistry at Princeton University. Just to give you a second of background before you get started here. Although when people ask me where I'm from, I tell them New Jersey these days. In fact, I spent the first 22 years of my life in LA. I was an undergraduate at UCLA, so I'm somewhat familiar with the area. And then after graduating from UCLA, I went to the East Coast, where I've stayed. But the first stop was MIT for my graduate work, and I was in Mark Wrighton's group doing photoelectrochemistry with various people. But one of them that showed up about a year after I arrived at MIT was Nate Lewis. So I had the pleasure of teaching him a little bit about photoelectrochemistry, actually. And that is actually a subject that I'm going to try and stay away from this term. We're going to deal with the other aspects of electrochemistry, since Nate has a wonderful course going on if you want to hear about that. So we'll think about things that happen at metal electrodes, and stay away from semiconductors, unless you want me to talk about semiconductors a little bit. I don't know. We can arrange that. What I'd like to do is, the course textbook is Bard and Faulkner's book, which is now in its second edition. This is a great book for learning the physical chemistry of electrochemistry. It's the second edition is much better in terms of examples, also actual real-life molecules that you might do something with. A dramatic improvement in the book there, so it's good from that. It's not really good if you wanted to kind of go into the lab and do an experiment and wanted to know, how do you do this? Kind of a hands-on